All right, welcome to Recitation 7, MAE 242 on the day before spring break. We're all super, super excited to be here. Okay. Anyway, this is a fairly decent lecture, recitation come to. We're going to be covering Bernoulli's principle and energy equation. So it's, pretty worthy subjects. First one, this one will have to do with Bernoulli's principle, which, if you're unfamiliar, the professor should go over it with you at some point here very shortly. But essentially, you take all of these, your mass, momentum, energy equations, you can basically make all these assumptions for them, where if the flow is steady, inviscid, uniform, incompressible, all that stuff, you get these collections of terms that all add up to a constant value along a streamline in some fluid. So we can use that, and it's really useful for a lot of applications like this. So for this first one, we have a jet of water discharges vertically from a nozzle with an exit diameter of 2 centimeters and a reservoir water level 2 meters above the nozzle outlet. The jet supports a plate with a mass of 0.5 kilograms. Find the distance from the nozzle to the plate if the system is in equilibrium. So we want to find this little h value right here, right? Want to find that h. Okay. So first things first, if we're particularly smart and astute about this, and I'm not going to write my assumptions down, since we're going to be using Bernoulli's principle, it's already, it's got to be steady, inviscid, incompressible, uniform, all that stuff. There's no like work being done on the fluid, right? So, if you look at this whole problem, you can see, okay, we're going to label some points here that we care about. So this will be point one right there. This some point right at the nozzle exit, we'll call that point two. Let me zoom in a little bit. We'll call that point two, and then some point right hitting the plate, right where the water hits the plate, we'll call that point three. Okay. Now, if you look all along this, in this whole system, these 3 points all lie along a streamline, right? They're all like connected by the same streamline. So if you think if you're some fluid element riding along the streamline, you can get to all 3 points, no problem. So, the most important thing we need to find first is the water is coming out of it's coming out of the nozzle at some velocity v2, right? Um, so what we can do is we can use we don't really know anything about point three right now, other than that it's touching the plate. So we have to find some relation between point one and point two. And to do that, we can use our Bernoulli's equation, which looks like this. Right. I know my rows. Those are rows. That's density right there. Where we can just use density of the water is 1,000, right? Um, and so we can make some additional assumptions right now, right? And you can see so these terms on the left, right, since everything here is equal to a constant, you can set them equal to each other along the streamline and make relations with that. So let's make some assumptions. We can say P1 equals P2, because they're all open to atmosphere, so those will cancel, right? Or we can call them zero because it's open to atmosphere, so it's fine. So those go away. We can also say since this V1, right, is a giant reservoir, you can think of it like when you're trying to drain a lake out of a pipe, right? The velocity of the surface of that lake is basically zero. So you can say V1 equals zero. So that'll go away. And you can also say Z2 is our datum point. So we can say Z2 equals zero. Right, so that goes away. So now all we have is Z1 equals V2 squared over 2G. Pretty easy little relation. You know Z1 and you know G. G is just gravity. So we can say 2 equals V2 squared over 2 times 9.81. Solve for V2. Get V2 equals 6.264 meters per second. Cool. So obviously we're not done though. So now next thing we need to know is so if we're, you know, again, like since we're dealing with some system and equilibrium, right? Whenever you hear equilibrium, you want to think forces. So how do we get forces? We have to use conservation of momentum. So you know you're gonna have to do that. But next step is, okay, what do I want to draw as my control volume? I don't necessarily want to draw it. So obviously, you know, it's going to have to encompass some part of the plate, right? Because that's the external force bit we're going to be worried about. But you want to say, okay, how much of that little fluid outlet flow do I really want to include in this? Because you know, just from logic, that point 2 and point 3 aren't necessarily going to have the same velocity, right? Because as it leaves the nozzle, you've got some gravity pulling on that fluid. So it's not going to be, we can't assume that it's the same velocity. And also, just from Bernoulli's principle, you know it can't have the same velocity because of this whole relation, right? If you point 3 is at a higher elevation than point 2, so it can't have the same velocity, right? So we go, okay, how do we want to do this? So the smart thing to do would be to include some control volume that just barely touches the plate, right? If you can see that, you'll see it on the key. So now with that, we can use our momentum equation, and we just have one little inlet right where the velocity, or right where the water is touching the plate, with a diameter of the nozzle. We can call that's fine. We can make that assumption, and we don't really care about the area of the plate. We just care about the area of the inlet, right? Which is just the diameter of the nozzle, area of the nozzle. So let's do our conservation of momentum. And I'm not going to write the whole thing out. You guys get the idea. We're on the left-hand side. The only external force we have is the weight of the plate pushing down, right? So we have negative W, right? And, you know, we have our coordinates here. And we don't care about anything in the x direction, right? We're assuming that the plate can't move left and right. It's just moving up and down. So we have negative W equals, we have just one inlet because those outlets are in the x direction, so we don't care about them. Negative rho v3 squared over a, right? And I'm going to drop the negative signs. It doesn't matter. Where w is just 0.5, right? That's the mass of the plate times 9.81 equals, I already dropped that. So equals 1,000. We're just calling density 1,000. v3 squared times, what's our area? It's just pi times 0.02 squared over 4. Okay. Solve for v3. We have v3 equals 3.951. And for what it's worth, I think the key has this wrong. I was looking at the key, and I don't think they ever squared this velocity term in here when they did the math. So their number's off by just a little bit. I don't think it's appreciably different. Their final answer is off, obviously, just by a little bit, but the concept's all there. If you need to go back and look at the key, the concept's there, the equations are there. It's fine. They just flubbed a little number. Well, that's okay. All right, so now we're in business. So if you think now, what are we ultimately trying to solve for? We're going to solve for some change in height right here, right? Little h. We want to solve for little h right there that I wrote very poorly. So how do we do that? Well, we know everything's open atmosphere again. So technically speaking, we know the pressures at these 2 points. We know the velocity is at 2 points, and we want to solve for some height. Well, go back to Bernoulli's for 2 to 3. Right, so let's rewrite it. Right, so now it's just back to the basics, just like we did before, where P2 and P3, they're both open to atmosphere, so we can say their pressures go away. Z2, we can call that our datum point, so that goes away. And now we're just left with a bunch of stuff we already know. So we're left with V2 squared over 2G equals V3 squared over 2G plus Z3, which is the height we're solving for. So plug everything in. We get yada yada. What's our V2 is 6.264 over 2 times 9.81 minus V3 and that equals Z3. And Z3 equals H equals 1.204. Cool. And, a little sanity check, right? Um, Obviously, if we're just using gravity and we have some external force, the final height has to be somewhere between 0 and 2, right? If you get something bigger than 2, you probably messed up because since there's no pumping action going on from here to here, you can't get back to the original level. It's just physics, right? Especially if there's an external force pushing you down, you can't get back to where you started. So that's cool. I think in the T it has like 1.6, so still within the realm of possibilities. So the concept's all there if you need to go back and look at it, but just be careful with the algebra. But the concept, yeah, I mean, this is Bernoulli's equation. If everything lies on the same streamline, you can make some money. You can get some stuff going. Start looking at what you know, what you can cancel, all that good stuff. Cool. Any questions with that? Pretty chill. Cool. All right. Let's keep moving. Let's get out of here pretty quick. Question 2 has to do with the energy equation, which is used pretty sparingly, actually, in this class. Sparingly enough that I always forget what the equation actually is, but whatever. It'll be fine. So for problem 2, we've got a power plant is next to a river. It steadily pumps some water into its cooling system and dumps the heated water back into the river. When running at full capacity, it rejects 50 megawatts of waste heat into the river. Use rho equals 1,000 and Cp, the specific heat at constant pressure, is equal to 4210 joules per kilogram Kelvin. Those of you who like thermo should understand this problem pretty well. It's a very thermo-y problem. For A, upstream Q, the volume flow rate, and temperature is 10 degrees Celsius. Volume flow rate is 2.5 cubic meters per second, and temperature is 10 degrees Celsius. So what is the temperature far downstream, right? So after everything's already mixed, and the river drops a distance of 5 meters. So let me draw what's actually going on here. It'll be something like this. And this problem's a classic. I've had this problem every semester I've TA'd for this class. And even when I took this class, we even had it. So this thing's been on here for at least 2 years for sure. So I know what's going on here really well. So it's kind of what we're looking at here. We've got some sort of little power plant thingy. Right. We've got some inlet flow, some outlet flow. Got some delta Z. Ooh, that was a horrible delta. Jeez. Some change in height, right? And for it'll be apparent for part B why I'm going to write this, but for this part, assume that the water flowing into the power plant and the water flowing out has no delta Z. Occurs at the same level. Okay, that's kind of irrelevant for this first part, but it'll be cool for later. Okay, so let's get going. So first off, let's write our actual energy equation, at least in the form where we're already taking off the d by dt term, right? There's no time derivative going on here, so I'm not even going to write it. All right, and so we've got Q dot, that's our heat, right? That's our like heat flow, that's our megawatts, whatever. W dot S, that's our shaft work. So if there was some like turbine in here or something like that, some turbo machinery, that would be that term. And then W dot V, that's like viscous work, like friction stuff. But for the scope of this problem, those are both 0, so we can get rid of those right away. And now, like I said, we're already getting rid of the d by dt term. But our control surface term is P over rho plus V squared over 2 plus GZ plus U, where U is like internal energy, right? Times rho V dot N ds, right? But I prefer writing it, and you know, like this rho V dot N ds, that just turns into the rho VA term that you know and love once you do all the assumptions that we're going to make. But I like writing this better as P over rho plus U equals CP times temperature. Because boy, look at that. They give us a CP and they give us a temperature. So why the hell wouldn't you write it like that? You know? So let's get going. So you know, after making all the assumptions we want to make, right? It's steady inlet, steady outlet, you know, inviscid, all that stuff. We can just simplify this down into Q dot equals, all right, so what's leaving, right? That's the positive term. So what's leaving? We've got some CPT plus V squared over 2 plus GZ times, so you know it'll be a rho VA term, right? It'll be rho VA times something. But what's rho VA? Well, VA is just Q. It's our volume flow rate with a spare rho floating around there. So I'm just gonna write rho times Q because we're given a volume flow rate, so it's cool. And that's out, and then minus the same thing coming in. It's rho Q, but coming in, right? And so now what can we say? Well, so we know rho is a constant, Q is a constant, CP is a constant. And we can also say, since this stuff's occurring like, you know, super far upstream and super far downstream, we can say the two velocities are the same, so we can get rid of those, right? Because, you know, V in equals V out. So when you go and math everything out, right, you end up that they just cancel each other out. So that's cool. We can also say, since this is our delta Z, we can say that Z out equals 0, right? So that can go away. Okay. And so now we can just plug in. We want to find, we just want to find T out, right? That's what we're solving for. Let's go Q dot equals, the only term left in here is, you know, CP T out times rho Q minus, we still have this rho Q in here, times, you know, CP Tn plus GZ, right? Where we know our Z is just our delta Z. That's the 5 meters. So go plug everything in. We got 50 times 10 to the 6th equals 1,000 times 2.5 minus. I know I could factor things out a little better. Who cares? And it's just good practice to put everything into Kelvin. Since we're dealing with like a delta T, I don't think it really matters, but I solved everything in terms of Kelvin, then reconverted. That's just the best way to go about doing it. So 10 degrees Celsius in Kelvin is 283. Let's multiply by 283. Now plus G is just 9.81. And Z is 5 meters. So boom, plug everything in. Okay, T out ends up being 287.7 Kelvin, which is 14.7 degrees Celsius. Cool. So that was part A right there. Right? And so that's pretty easy. So for that volume flow rate of water coming in, the total heat downstream, right? The delta T downstream is 4.7 degrees. It heats the water up 4.7 degrees. Okay. So now let's move to part B. where regulations do not allow the plant to heat the water more than 10 degrees Celsius, right? So we heat it at 4.7 degrees. Well, we can only allow it to heat the water 10 degrees Celsius. So the actual temperature must not exceed 20 degrees. So we're still cool for now. But what is the minimum Q, minimum volume flow rate, to meet this requirement, right? So we've got 2.5. So 2.5 is good. So we're looking for a number smaller than 2.5. How far can we crank this thing down and still be within the regulations? So that's what we're doing. We're using the same exact equation, but just solving for Q now, because we know the delta T. We know the out is 20, and we know the in is 10. So same exact thing, right? So let's get going. So for part B, I'm just going to rewrite this whole equation, right? This same thing, it's the same exact equation. So Q dot equals these equations get very repetitive, but that's okay. Right, we're solving for this Q. And so now how I wrote this delta Z here for this part, this is 0. This is where this comes in handy, because we're assuming, like, if we're taking the little teeny tiny control volume right in here or whatever, we're assuming that it's just like two pipes like side by side, right, where it's coming in and just going out right at the same level. And so there's no delta Z there. So for that, we can say, since those are both 0, we can cancel those right away. And we also say the same thing with the velocities. Velocities are the same, just as last time. So we can say V out equals V in, and Z out equals Z in. So really, this equation becomes very, very easy. So we have Q dot equals CPT out, right? Rho Q minus CPT in rho Q. Clean up some equations, factor some stuff out. Q dot equals CP rho Q T out minus T in, which is our delta T, right? And so, this is 10 degrees, right? So plug in everything. We get 50 times 10 to the 6th equals 4210 times 1,000 times Q, which is what we're trying to find, times 10, right? And this time it doesn't matter if we convert Kelvin or not, because it's the same unit step, right? You don't care if it's Kelvin or Celsius, it's the same size of degree, okay? So go plug in for Q, solve for Q, whatever. You get 1.19 cubic meters per second. Which again, a little sanity check, makes sense. That number is smaller than what we had before because we have a higher delta T. So for that volume of water, and we're pumping out the same amount of heat, right? For that volume of water, we'll get a delta T of 10 degrees exactly. So pretty cool, pretty cool. Any questions? That said, very, very thermo-y. If you're familiar with thermo, if you've already taken that, this should not be a huge step for you. But anyway, if you have any questions, shoot me an email. And with that, should be good to go.